All right, AGS1, we are back with 6.6, and we're going to talk about, is this regular? Regular is going to be a big word today because we're only going to be looking at regular polygons. The essential question for the day, what is regular? About a regular polygon. How does this connect to symmetries? So today we're going to talk symmetries, both rotational and reflectional, and we are going to look at a bunch of polygons. So first, that word regular, a regular polygon, the regular part of it, well, let's first talk about the polygon part. The polygon part means that it has all straight sides that are, it's a closed figure, so it's not open, and every side is congruent to the other side. So no sides are bigger than another. So something like an isosceles triangle would not be a regular polygon because there's two sides of the same, but the third side is not. Another big feature of regular polygons is that all the interior angles are congruent. So all the sides are congruent and all the interior angles are congruent. Let's look at a regular triangle. Now you might look at that and be like, Mr. Jolly, why are you calling that a regular triangle? That's an equilateral triangle, which is absolutely true. So like a regular triangle, people usually call an equilateral triangle, just like a regular quadrilateral is like a funny way of saying a square. Like a regular quadrilateral is all four sides are the same and all the interior angles are the same. And the only way that happens is with a square. Past that, like, pentagons, hexagons, septagons, and things like that, you would just say regular this, regular that, whatever. So, you guys, looking at this regular triangle, let's first talk about lines of reflection. So, I think from here on out today, I'm going to make any pink lines I do are going to be lines of reflection, which means that you could fold it over that line and it would perfectly match up with itself. And then any green lines I do are going to be lines of rotation. They're going to have to deal with rotational symmetries. So, when I first look at this regular triangle and think about the lines of reflection, the first line of reflection that my brain sees is that you could take this image and cut it right down the middle where this hits at a 90-degree angle and fold it over itself. And, this side would match up with this side and this part would match up with this part. So that is a line of reflection. But it's not the only line of reflection on this triangle. There's two more that you could, also take this corner and then bring it over to this side at a 90-degree angle. And that's another line of reflection where this side would match up with this side if you fold it, and then these bottom parts would also match up with each other. So that's another one. And then the third one is through the third vertex. So it goes through a vertex, and then it goes to the midpoint of the other side, because this point right here would split this side in half. In fact, it would split all these sides in half. So these would all be congruent. So, symmetry. We have three lines of symmetry. All of these lines of symmetry connect a vertex to the opposite midpoint. So that's all the symmetries of the regular triangle. Now let's switch to rotational symmetries. So I'm going to try to rotate this figure, but it probably won't work out perfectly. You guys, if you think about this whole triangle being inside a circle, you could rotate it a certain amount between 0 and 360, and it will match up with itself before you get back to 360. Let me take that circle away. I think here I can try to rotate it and we'll see what happens. I guess, what's the best way to do this? Oh, it's drawing on the figure. Okay, Miss McNeely was better at this. She was smart to have two pictures of it. I'm just going to draw. That's my strength. You guys, if you take this corner right here and then you rotate it all the way to this corner, you will get the same triangle again. So the question is, like, how far did that rotate? Well, if you think about the triangle being inscribed in a circle again, that's 1/3 of the circle that you're rotating through. So if you take 360 degrees and divide it by 3, which is the sides of the triangles, there will be a 120-degree rotation here. So if you take this and rotate all the way to here, that's 120 degrees. If you were to take this point and rotate past the 120 and then all the way around to this point right here, this would be 120 degrees. So this would be a 240-degree rotation. Now, if you were to take this point and go a full 360, yes, you would get the same figure again, but 360 rotations are nothing special, because any object or polygon you could rotate 360 and you'll get the same thing again. So we don't usually talk about the 360 ones because they're not unique. Anything does that. So in terms of rotations, around this center point, so this point right in the middle where all those lines of reflection cross, if you're rotating about that point, you'll get the same triangle again if you turn it 120 degrees and 240 degrees. So yes, there are rotational symmetries, and they are at 120 degrees and 240 degrees. Once again, the trick to figure out how far that rotated is just to take a full circle and divide by how many sides there are. The next thing we are going to look at is a regular pentagon. So I'm going to switch back to pink because I want to talk about the lines of reflection first. So similar to the regular triangle, the equilateral triangle, if you take a vertex and then draw a dashed line connecting it to a midpoint of the other side. So if this splits this side completely in half, you could fold this half of the pentagon over and it would match up perfectly with this side. So that pink line is a line of reflection. So that's one of them, but that's not the only one. Oh, sorry, I should have talked about, let me talk for a second about why this is a regular pentagon. I know when people say pentagon, this is the shape you think of, but technically any five-sided shape is a pentagon. So if I'm like 1, 2, 3, 4, 5, like this is a pentagon as well. It's just kind of a weird one. Well, it's not weird, but it's a pentagon, but it's not a regular pentagon. A regular pentagon means that all of these sides are the same, they're congruent, and that all the interior angles are also congruent. So I would say this angle is the same as this angle, is the same as this, is the same as this, is the same as this. So back to my lines of symmetry, I connected a vertex with a midpoint and found that line where you can fold it over. But that's not the only one. In fact, there's one that goes through here that connects a vertex to a midpoint. There's one that connects this vertex to a midpoint. One that connects this vertex to midpoints. And there's one more that connects this vertex to a midpoint. So in terms of symmetries, there are 5 lines of reflection. Once again, these are connecting a vertex to an opposite midpoint. Now let's switch to green and think about the rotational symmetries. So let me see. If I rotate this, like if I rotate it to here, that kind of looks like the same pentagon again. Like if I, this and this are the same pentagon. So I rotated, you know, this far and got the same one again. So let me put that in green, that if I take this point and rotate it around this center point where all those lines of symmetry cross, so if I rotate it this far to here, you'll get the same pentagon again. But it's a good question about how far that rotates. If you think about this pentagon being inscribed in a circle, if I take this angle, right, well, stop, go back. If I take this angle right here, do you see how this is one pizza slice out of 5 pizza slices in the entire figure? So the entire figure is a full 360 degrees. So if I want to know just this angle right here, or which is the same as how far this rotation is, you would take 360 and divide it by 5. So if you take 360 and you divide it by the 5 sides, you get 72 degrees, which means this rotation is 72 degrees. If you take this point and rotate it past the 72 all the way to this point, that's 272 degrees, which is what, 144 degrees? Then if we go 72 more past that, you know, taking that top point and rotating, so go start here again. That dot's going to get very big by the end of this. Go past the 144 to this point right here. That's going to be another 72 on top of the 144 is 216 degrees. Then there's one more where if I start here at this giant dot now and rotate it past the 72, past the 144, past the 216, all the way to here, that is going to be a total of 288 degrees. And then the last one would be a full 360, but once again, who cares? So the rotational symmetries, yes, they occur. They are at 72 degrees, 206, nope, skipped one. 144 degrees, and 216 degrees, and 288 degrees. So that's all the reflectional symmetries and the rotational symmetries of a regular pentagon. Notice that it's a 5-sided regular shape, and there are 5 lines of symmetry and 1, 2, 3, 4 lines or rotationals. Let me see, back on the triangle, triangle has 3 sides. There was 3 symmetries, and we had 1, 2 rotations. So 3 sides, 2 rotations, 5 sides, 4 rotations. Perhaps there is a pattern emerging. Let's do it all again, but we're going to go a little bit quicker now that we're in the swing of things. This is a regular hexagon. Perhaps you've seen this in nature. Bees are a big fan of this one. There's a lot of symmetries with this one. Let's see. One symmetry we could do is we could connect midpoint to midpoint. So if I connect these 2 midpoints, that would create a line where if I fold this side over, it's going to match up perfectly with this side right here. So that's a line of symmetry. But there's lots of those. I could connect all the midpoints of the sides. So, you know, here's another one. That's 2. And then midpoint to midpoint again. So we're up to 3. But with a hexagon, that's not the only symmetries. You could also connect vertex to vertex. So if I draw a line to opposite vertices, that will also create symmetries. So we have a grand total of 1, 2, 3, 4, 5, 6 symmetries in a hexagon. So let's say symmetries that we get 6 lines of symmetry. There was 3 vertex to vertex, and also 3 midpoint to midpoint. Now, rotational symmetries. Once again, if you picture this whole thing inscribed in a circle, and then you were to grab it and turn it, do you see how, like, if I turn this far, I'll get the same hexagon again? So it's like here, the top and the bottom are like, you know, parallel to the x-axis, and then here it's also parallel to the x-axis, top and bottom. So that rotation, if I take, you know, this corner, it doesn't matter which one, you could grab any corner, but if I rotate it this far to this corner, I'll get the same hexagon again. So to figure out how far that is, take a full 360 and divide it by how many sides there are, which mean each of these are 60 degrees. So this would be 60 degrees, and then this here would be 120 degrees, then here would be another 60, which is 180 degrees. That makes sense because it's a half circle. And then another 60 is 240 degrees. Then that's 300 degrees. And then the next one would be a full 360. So let's see, symmetries, no, rotations. There are how many of them? Let's see. 1, 2, 3, 4, 5. Seems like it's always one less than the sides of the polygon. So yes, we have rotations. They are at 60 degrees, 120 degrees, 180 degrees, 240 degrees, and 300 degrees. So there are 1, 2, 3, 4, 5. Last one I'm going to do with you guys, a regular octagon. Let's see if we can do this one super quick. Let me see. Notice that I skipped the septagon. So it goes like pentagon, hexagon, septagon, octagon, nonagon, decagon. I'm going to leave it as part of your homework to Google what an 11-sided gon is, because that's a fun word. And then the 12 is a dodecagon. Then anything past that, you would really just call like a 13-gon or a 14-gon. There might be some Latin names for them, but really past dodecagon, like we don't really say the Latin after that. Okay, let's see. Vertex or midpoint to midpoint. This is a line of symmetry, so I could connect all of those sides. So that's 1, 2, 3, 4. 4 of those. But similar to the hexagon, I can also connect vertice to vertices. So, or vertex to vertex, excuse me. So that's 5, 6, 7, 8. So we got 8 lines of symmetry for the octagon. That makes sense. And notice they all cross at this center point here. So symmetries, got 8 lines of reflection. 4 of them are vertex to vertex. And 4 of them are midpoint to midpoint. Now, let's talk about rotations. If I grab this corner and turn it this far, I'll get the same shape again. So if I take 360 and divide it by 8, what is that offhand? Oh, that's 45 degrees. That makes sense. So this would be 45, and then this would be 2 45s, and this would be 3 45s, and 4 45s, and 5 45s, and 6 45s, and 7 45s. So the rotations, yes, it has rotational symmetries, and they are at 45 degrees, 90 degrees, 135 degrees. What's the next one? 180. 180 degrees, 225 degrees, 270 degrees, 315 degrees, and then I think the next one would be 360. Let me see how many we got. 1, 2, 3, 4, 5, 6, 7. Yep, that's one less than this shape. Size of the shape. Okay, you guys, Mr. Jolly, me, I'm also going to play or Miss McNeely, I'm not sure who's talking to you right now, is going to play a Nonagon video for you guys right now, which is a super fun song about a Nonagon.